Okay, let's talk about particle orbits when the force field changes. Here's the question we are looking at. Imagine a particle moving in a nice circular orbit under a force field given by F vector of r vector equals minus k over r squared r hat, where k is a positive constant. Now what happens if this force suddenly changes? It switches to F vector of r vector equals minus k over 2 r squared r hat. The question is, what would the shape of this new orbit be? And we have four options: 1 parabolic, 2 circular, 3 elliptical, or 4 hyperbolic. So first let's understand the starting point. The particle is initially in a circular orbit under that original force field. F vector of r vector equals minus k over r squared r hat. This type of force, where the strength depends on 1 over r squared and it's attractive because of the minus sign, is a classic inverse square attractive force, like gravity or the electrostatic force between opposite charges. Step 1 is to figure out the particle's initial kinetic and potential energy while it's in that comfortable circular orbit. For a circular orbit under an attractive center force like this, the force pulling the particle towards the center is what provides the necessary centripetal force to keep it in a circle. The magnitude of the force is F equals k over r squared. The required centripetal force is F sub c equals mv squared over r, where m is the particle's mass and v is its speed. For that initial circular orbit, these two must be equal. So mv squared over r equals k over r squared. If we multiply both sides by r, we get mv squared equals k over r. This is a key relationship for a circular orbit under this force. Continuing with step 1, let's get the initial kinetic and potential energy explicitly. The initial kinetic energy T is simply 1/2 mv squared. Since we just found that mv squared equals k over r, for the circular orbit, we can substitute that in. So T equals 1/2 times k over r, which simplifies nicely to k over 2r. Now for the initial potential energy U. For the force field, F vector of r vector equals minus k over r squared r hat. The potential energy U of r is given by the negative integral of the radial component of the force with respect to r. That's minus the integral of minus k over r squared dr. When you perform that integration, you get minus k over r. So the initial potential energy U is minus k over r. Step 2 is to calculate the total energy of this initial circular orbit. The total energy, let's call it E1, is just the sum of the initial kinetic energy, T, and the initial potential energy, U. So E1 equals T plus U. Plugging in the expressions we just found, E1 equals k over 2r plus minus k over r. Combining these terms, k over 2r minus k over r, A gives us minus k over 2r. Since k is a positive constant and r the radius is also positive, E1 is a negative value. A negative total energy is exactly what we expect for a bound orbit like a circle or an ellipse. Step 3 is where the interesting part happens, analyzing the effect of that sudden change in the force. The force suddenly changes to F prime vector of r vector equals minus k over 2 r squared r hat. Notice the force is now half as strong at the same distance r compared to before. The phrase suddenly changes is really important here. It tells us that at that exact instant, the force changes the particle's position. R does not have time to change. It's still at the same distance from the center. Also, the particle's velocity vector v does not change at that instant. It's still moving with the same speed and in the same direction it was in the circular orbit. Consequently, because the velocity doesn't change its kinetic energy, T remains exactly the same at that moment, and also its angular momentum L remains the same. Alright, step 4. We need to calculate the new potential energy and then the new total energy for this new force field. The new potential energy U prime for the force field F prime vector of r vector equals minus k over 2 r squared r hat is calculated the same way as before, minus the integral of the radial force component. That's minus the integral of minus k over 2 r squared dr. Integrating this gives us minus k over 2r. So the new potential energy U prime is minus k over 2r. Now remember what we said in the last step, the kinetic energy T prime remains unchanged at the instant of the force change. So T prime is still equal to the original kinetic energy T, which was k over 2r. The new total energy, let's call it E2, is the sum of this new kinetic energy T prime and the new potential energy U prime. So E2 equals T prime plus U prime. Plugging in our values, E2 equals k over 2r plus minus k over 2r. And look at that, this adds up to exactly 0. Finally, step 5. Determine the shape of the new orbit based on this new total energy. For an inverse square attractive force field, like the new one, F prime vector is still proportional to 1 over r squared. The shape of the resulting orbit is completely determined by its total energy, E. Here's the rule. If the total energy E is less than 0, the orbit is elliptical. A circle is a special case of an ellipse. If the total energy E is exactly equal to 0, the orbit is parabolic. And if the total energy E is greater than 0, the orbit is hyperbolic. Since our new total energy E2 came out to be exactly 0, the shape of the new orbit would be parabolic. So just to conclude, after the force suddenly changes, the new total energy of the particle is E2 equals 0. For an inverse square force field having a total energy E equal to 0 means the orbit is parabolic. Therefore, the final answer is parabolic.